It's time for Fun with Math, and today we are going to go back and re-explore some ideas about limits. And so let's start off with a review of limits. So remember, the idea of a limit is as the input gets closer and closer to some number, in this case 3, we ask the question, what does the output get closer and closer to? And if the function is continuous, we can simply just plug in the point and get the answer. So let's just try to plug in the point. And so you get 3 squared minus 3 plus 5, which is equal to 9 minus 3, which is 6, plus 5, which is 11, which is a good answer. So if you look at the graph of this function, what you'll notice is as you get closer and closer to 3, the graph, the output, gets closer and closer to 11. Let's try the function next to it here and see what happens. So let's plug in 3 here, and what do we get? We get 3 squared minus 9 divided by 3 minus 3. And this time, we get out an answer that kind of doesn't make any sense. We get 0 over 0 out. And so remember, this was this indeterminate form, which means you can't determine the limit as given. You need to do something else, basically. It may exist, it may not exist, we're not quite sure yet. So one way to handle this type of problem is we just do a little bit of algebra. We're just going to factor this top here. We're going to factor the numerator. So this will be equal to the limit as x goes to 3 of, and on top you have x plus or minus something, x plus or minus something, and then divided by x minus 3. And of course, to figure out the somethings, you look at the 9, and so you're guessing probably 3 and 3. And there's no middle term, so that's why this is plus and this is minus. And so you see in this function, the reason when you plug in 3 you don't get an answer is because you actually have a hole there. So it's not continuous there, but we can cross these off because limit-wise, these expressions are the same as you go to 3. And you get this to be equal to then the limit as x goes to 3 of x plus 3, and so now we reevaluate the limit by plugging in 3, and we get 3 plus 3, which equals 6. So sometimes you simply just plug in the point and get the answer. Sometimes you plug in the point and you get out what we call an indeterminate form, and so then you have to go back and kind of rework the function a bit and see if you can't get out an answer. Let's go down here to the next spot, and let's take a look at this limit. So the limit as x goes to 1 of this expression. So let's plug in 1 and see what happens. So you get a 1 here, minus 2 plus 1, so you get a 0 on top. And then on bottom, you get a 1 minus 2 plus 1, so you get a 0 again. So another indeterminate form. And so how do we handle this type of indeterminate form? Well, just like we did before, we're hoping that we can factor the top and factor the bottom and try to get an answer. So let's see what happens here. So we get this to be equal to the limit as x goes to 1. And it would be x plus or minus something, x plus or minus something. And so here I'm thinking it's probably minus 1 and minus 1. And then on the bottom here we have an x. And then here we can factor out an x and we get an x squared minus 2x plus 1. Oh, hold on a second. So I didn't have to factor the top. I could leave the top alone because it looks like the bottom is going to be exactly the same here. So we will just cross off the top and the bottom. So top and bottom. The x stays, and so this leaves us with the limit as x goes to 1 of 1 over x, which of course is equal to 1 divided by 1, which equals 1. So this is another example when you try to plug in the point 1. You get out an indeterminate form, which probably means the function's not continuous here. And when we factor, we see, oh, it actually has holes at 1, x equal 1. And so you can cross out the top and bottom here, leaving the x on the bottom. Then we reevaluate the limit and get back 1. Now let's look at this one, because this one's a little bit different. When you plug in 0, you get cosine of 0 minus 1, which is 1 minus 1. So you get 0 divided by, of course, a 0 on the bottom. So another indeterminate form. But when we try to determine this limit, we can't use factorization because we can't factor cosine of x minus 1. So the only thing that we have left that we can do is we can make a table. So let's make a table using this function. So we have x here, and then cosine of x minus 1 divided by x. And so we're going to have to use our calculator. In a little bit, I'm going to show you how you can use something called L'Hopital's rule to figure this out using calculus. But right now we'll use our calculator. So the idea is plug in a point close to 0. So like plug in point, I don't know, let's say 0, 0, 1. We'll do it from the right and we'll do it from the left. So we'll also do negative 0.001. So you can see what I'm plugging in. I'll write down here cosine of 0.001 minus 1 divided by 0.001. And then on my calculator, it'll tell me approximately what this is. So let's check it on here. So hopefully you remember doing some of this stuff. We'll do left parenthesis cosine. Oh, I better make sure I'm in radians. So I am in radians. So cosine of 0.001 in parenthesis, and then take away 1 in parenthesis. And then we're going to divide by 0.001. Hit enter, and out pops a number, negative 4.99996 e to the negative 4. So remember, this big E means times 10. So times 10 to the negative 4 means take that decimal place over 4 spots. So basically, this number is 0. If you do the same thing with negative 0.001, we're going to get out something that's also approximately 0. To see that, we can just hit second entry, and then wherever you see this 0.001, we'll insert a negative sign. And so over here we can insert a negative sign, but you're going to get out the same answer basically, which is approximately 0, right? This time it's positive, but it's 4.999 e to negative 4, which is times 10 to the negative 4. So it's like 0.000049996. All right, so here we'll write approximately 0. All right, so in this one, a little bit different because we couldn't use any sort of algebra. We had to use a table in our technology, but we will learn a way to do this with calculus so we don't have to depend upon our calculator. All right, so these were what we might call finite limits, or limits when x is going to a finite number. Down here we have kind of infinite limits when x goes to plus or minus infinity. So let's take a look at these. So I can remind you how we work these types of problems. So notice if you plug in infinity, just so you can see, you'll get infinity on top, infinity on the bottom. So infinity over infinity is another type of indeterminate form. So I just mentioned this briefly when we went over it about a month ago. But it's another type of indeterminate form, which just basically means, you can't just plug in quote, quote, the number and get the answer. You have to do a little bit more work. So on this one, what we did, we said, well, look, since you're going so big, infinity is such a quote, quote, big number, you can cancel off the lower degree terms on top and keep the large degree term in the numerator, and the same thing in the denominator. You can cross off the lower degree terms and keep this highest degree term. So this limit should be the same as this limit here. The limit is x goes to infinity of 3x squared over 2x squared. And this only works if you're going to plus or minus infinity. And so then, of course, these x squareds are going to cancel because you have an x squared on top and x squared on bottom. And so this will be equal to the limit as x goes to infinity. And notice you keep the limit on there until you actually evaluate it, until you actually kind of plug in the number, right? Here it's in quoting, the number's infinity, but the idea now is like, hey, as x gets bigger and bigger, what does this thing do? It stays the same. So it's just equal to 3/2. It's just a constant. And so the answer to this question is 3 over 2. Remember, you can even check your work here. If you plug in a really big number like 100, you'll say you basically get 1.5 out. You know, you plug this into your calculator, put 100 here, and 100 there, and 100 there, and you'll get out basically 1.5, which is 3/2. Let's look at this problem, because this one is kind of similar to the one above it in a way. You plug in infinity, and you get infinity times sine of 1 over infinity. So let's write this down. This is going to give us another indeterminate form. And so this is infinity, and I'll put this in quotes, because really I'm kind of thinking here. This is infinity times sine of 0. So infinity times sine of 0, because 1 over infinity is like 0. And then sine of 0 is 0. So this is another type of indeterminate form. So infinity times 0. And we should talk a little bit about why it's indeterminate. Let's write this down. It's indeterminate form. And again, it's indeterminate means you can't determine the limit as given. And if you think about it, infinity times 0, the idea is like, well, which one's winning? Is 0 winning? If 0 is winning, then this thing will go to 0. Or is infinity winning? If infinity is winning, this thing will go to infinity. It'll beat out the 0. Or are they somehow behaving in a way that they cancel each other out, and this thing is going to go to a number? Same thing over here. Infinity or infinity is an indeterminate form because it's kind of like, is the top winning? Is the top infinity winning, or is the bottom infinity winning? If the top infinity wins, it'll go to infinity. If the bottom infinity wins, it'll go to 0. But maybe somehow these infinities are canceling each other out. So you see somehow over here, these infinities actually cancel each other out, and they're giving you 3/2. That's why we call these indeterminate forms. Just can't be determined as given. So on this one, you can't do any sort of algebra tricks or anything. What you have to do is you have to make a table so we can see what's happening here. So you have your x, and then we have this x sine of 1 over x. And we're going to infinity this time, so we want to plug in a big number. So you want to plug in like maybe, let's try 1,000 and see what happens there. So on our calculator, we'll plug in 1,000. And I guess I should write this out here so you can see what I'm doing. All right, so 1,000 sine of 1 over 1,000. And it'll be approximately, so hopefully when you plug this in, you can kind of tell what's happening. And so you get 1,000, and then sine of 1 over 1,000. In parentheses equals. And it's 0.99999983333. And so I would guess that the limit, what number is that getting close to? I would guess it's getting close to the number 1. So it's approximately 1. And so here, oh, and I never finished this off, right? So here I should write equal to 1 next to this. And up here, I should write this one equal to 0. I never finished off this problem. So this limit is equal to 0. This limit is equal to the number 1. And so that's a quick review of limits and talking a little bit more about indeterminate forms. So what we're going to do is we're going to do L'Hopital's rule. And L'Hopital's rule involves these types of indeterminate forms, 0 over 0, or infinity over infinity. And eventually we'll talk about these other indeterminate forms down here, but we'll wait a little bit on that. So what does L'Hopital's rule say? It's actually pretty simple. It says that if you're taking a limit as x goes to some number a of f of x over g of x, so this also works for plus or minus infinity too. It says then if you want to evaluate this limit and you get one of these indeterminate forms out, 0 over 0 or infinity, when you plug in a, what we can do is we can take the derivative of the top and divide by the derivative of the bottom, and then take the limit, and these two things will be equal to each other. So let's just take a look at an example, because this is actually pretty easy to do once you get the hang of it. So let's go back to our examples that we were working before, so I can show you another way to do these problems using L'Hopital's rule. All right, so let's just test it again for fun. You plug in 3, you get 0. You plug in 3, you get 9 minus 9, which is 0. So we have this 0 over 0, which is this indeterminate form. And we saw this before. And so now, though, instead of using some algebra, we're going to use L'Hopital's rule. And so L'Hopital's rule says if you get this form 0 over 0 out, that's what we're focusing on first, these 0 over 0 indeterminate forms. What happens is you can take, and let's write this, we'll use L'Hopital here, so L'Hopital. Some of the students like to say you take it to the hospital to get fixed. So here you have the limit as x goes to 3, and we'll take the derivative of the top. So what's the derivative of x minus 3? It's just 1 minus 0, so just a 1. Divided by the derivative of the bottom, and here that's 2x minus 0. And so then this is going to be equal to, it's going to be equal to what? 1 divided by, and then we have 2x, so 2 times 3, which equals 1 over 6. And so we get the same answer as we did before, and if we check that up here, I think on this one, oh, there I wrote them differently on here, didn't I? Oh, I see. All right, so down here, I meant to put that on top. I put that other one on top, but that's okay. All right, but so the answer is still 1, 6. It's just a matchup with the one that we did before. But that's L'Hopital's rule. You take the derivative of the top, divide by the derivative of the bottom, then you can reevaluate the limit, and you get back the answer. So you don't have to use any sort of algebra if you don't want to. Down here, let's look at part B. So we're going to do the same thing. If you plug in 1, remember you get 0 on top, 1 minus 2 plus 1, and you actually get 0 on the bottom, right? 1 minus 2 plus 1. And so then this is an indeterminate form. So let's practice writing the word indeterminate form, which simply means that limit can't be determined as given. And so now to determine this limit, what we're going to do is we're going to use L'Hopital. And I like to write L'Hopital here. You don't have to. You don't have to write L'Hopital. But I like to. I like to spell it La Hospital because, you know, I think to myself, oh, the limit's broken here. I got to take it to the hospital to get fixed. So L'Hopital's rule says you just take the derivative of the top, divide by the derivative of the bottom. I have the right form, so I can do that. So the limit as x goes to 1. The derivative of the top is a 2x minus 2. The derivative of the bottom is 3x squared minus 4x. Oh, and there's a plus 1 too. So plus 1. So just derivative of the top divided by the derivative of the bottom. And now I'm going to reevaluate this limit to see if I get a better answer. So I plug in. So I get 2 minus 2 on top, which is 0. And on bottom, when you plug in 1, you get 3 minus 4 plus 1, which is 0. Oh, I still have an indeterminate form. And so what can I do now? Well, you still have the right indeterminate form. You have that 0 over 0 form. So I can do L'Hopital again. So let's do L'Hopital again. So right here, all right. Hey, look, I'm doing L'Hopital. And I take the limit as x goes to 1. The derivative of the top is the number 2, divided by the derivative of the bottom, which is 6x minus 4, which is equal to, when you plug in 1, you get 2 on top, and then you get 6 minus 4 on the bottom, which is 2, which is equal to the number 1, which should match up with the answer we got before, if I wrote it down correctly, which I did on this one. All right, and remember, you can check your work if you want to. You could use a calculator and plug in like 1.001 into this expression, and you'll see you get out basically the number 1. Now, we had techniques to do these two before by using just, you know, basically factorization, an algebra trick. Down below, though, on part C, we couldn't do any algebra, so we had to rely upon our technology. But now we can use L'Hopital. So when you plug in 0 here, notice you get cosine of 0 minus 1, which is 0, divided by 0. So we have the right form. We have this indeterminate form. And so now what we can do is we can L'Hopital it. So this will be equal to, by L'Hopital, this will be equal to the limit as x goes to 0 of, and we'll take the derivative of the top, divided by the derivative of the bottom. And so the derivative of cosine of x, remember, is a negative sine of x, minus 0, and then divided by 1 on the bottom. And now you plug in your 0, so we reevaluate the limit now. So negative sine of 0, which of course is negative 0, which is 0. And so now we have a way to evaluate these types of limits without relying upon our calculator. So that was the 0 over 0 form. Let's do one with infinity over infinity form. So again, this is the one we did when we were reviewing, and I showed you how we did it when we first learned it. And so, but let's just, again, if you plug in infinity, notice you get infinity on top and infinity on the bottom. So we have this infinity over infinity form, which is a nice L'Hopital form. So it means we can use L'Hopital's rule, but it is an indeterminate form. So we have this indeterminate form that we can L'Hopital. So this will be equal to, by L'Hopital's rule, it'll be equal to the limit as x goes to infinity of, take the derivative of the top, so 6x minus 2 divided by 4x. Now notice, so you did the derivative of the top divided by the derivative of the bottom, but notice if you plug in infinity again, you get out infinity over infinity, which is another indeterminate form that you can L'Hopital. So we still don't know what the limit is using this rule, but we can just L'Hopital it again. So I'll L'Hopital it again. So limit as x goes to infinity, because it has the right form, infinity over infinity. Then the top is 6, because derivative of 6x is 6 minus 0, divided by the derivative of the bottom, which is 4. And so then the answer here, of course, is equal to 6 over 4, which reduces to 3 over 2. And that matches up with what we found before. So that's how you do limits if you have this infinity or infinity indeterminate form. So now we get to sort of the harder part of using L'Hopital's rule. What if the indeterminate forms are not 0 over 0 or infinity or infinity? So these are some other common types of indeterminate forms. We talked about why infinity times 0 would be an indeterminate form, like is infinity winning, 0 winning. You know, there's also this type of indeterminate form, 1 to the infinity. Okay, so if you think about that, if a number is bigger than 1, like 2, and you raise it to like the infinity, it's going to be basically infinity. But if you have 1/2 and you raise it to the infinity, it's going to be like 0. Right, so this is why that's an indeterminate form. Numbers bigger than 1, when you raise to big numbers, get bigger. But numbers that are smaller than 1, like between 0 and 1, if you raise to big numbers, they get smaller. So the idea is, does the 1 win? What does the infinity win? A similar thing happens here. If you raise something to the 0 power, you know, like 2 to the 0 or 3 to the 0, these are all equal to the number 1. But infinity is a really large number, so it's kind of like, is raising it to the 0 winning, or is infinity winning? And you got to figure out which case that is. And same thing kind of with 0 to the 0. Right? So 0 to the 0, it's kind of like 0 is 0, but if you raise something to 0, you get 1. So which one's going to win out? Or are they going to somehow, you know, combine somehow, all right, and give you out some sort of number? All right, so let's take a look. And I should say this, the way that we handle these is that we try to turn these indeterminate forms somehow into these types of indeterminate forms. And then we can use L'Hopital's rule. So let's look at some examples real quick. So here are some examples. We did this one together using our calculator. But you know, how do we use this using L'Hopital? So let's go down here. I wrote these out down here. And let's just kind of check them out. Let's plug in 0 again. So remember, when we plugged in 0 here, we got 0 times, oh, not 0, I'm sorry, infinity. So when we plug in infinity, you get infinity times sine of 1 over infinity, which is times sine of 0, which is 0. And so again, this is an indeterminate form, but it's not one of our nice types of indeterminate forms. It's not 0 over 0 or infinity divided by infinity. So our goal then is to somehow turn this indeterminate form into one of these types, either infinity over infinity or 0 over 0. And you can kind of choose which one you want to do. If you choose the wrong one, you basically wind up in a situation that's difficult algebraically. But let's look. So here, I want to change this infinity times 0 into either infinity over infinity or 0 over 0. So the thought that I have is I can mess around with this x a little bit. I'm going to leave this alone because I think it's hard enough as is. But I can take this x, and instead of multiplying by it, I can turn this into division. And if you do that, let me show you what you get. So what I can do is I'll write the sign of 1 over x on top. And then on bottom, I'll divide this by not x, but 1 over x, because these need to be the same expression. Right? So it's kind of similar to saying, okay, well, I have 2 times 4, or I could write that as 4 divided by 1 over 2. Now, I know normally you wouldn't do this, but we do it in this case because what's going to happen, it's going to take this indeterminate form, and it's going to turn this indeterminate form into that indeterminate form. And once we have that indeterminate form, we can use L'Hopital. So check it out. If you plug in infinity, you get sine of 0 on top, which is 0. And on bottom, you get 1 over infinity. So let's write this as 1 over infinity. And of course, 1 over infinity is like 0. So now we have that 0 over 0 indeterminate form. And so now what we can do is we can use L'Hopital. And so let's use L'Hopital on this. So this is going to be equal to, it's equal to what? The limit as x goes to infinity. Oh, and I should write out here, so your notes, we're using L'Hopital's rule. And so we take the derivative of the top. Now, the derivative of the top's a little bit tricky because it's actually a chain rule. So we'll take the derivative of the outside, which is cosine of 1 over x, times the derivative of the inside. Now, remember, derivative of 1 over x, well, remember, 1 over x is really x to the negative 1. So its derivative, I'll just draw an arrow here for its derivative, would be negative 1, x to the minus 1, which is minus 2. Or if you like, we could write that as minus 1 over x squared. So times negative 1 over x squared. And then all divided by, oh, the derivative of 1 over x, we already know that because x is negative 1, is also negative 1 over x squared. And then what's nice is that you have the same thing on top and bottom, and you're multiplying here. So what can you do with these two terms? You can just cancel them out. So these two terms are gone. And so this is going to be equal to the limit as x goes to infinity of cosine of 1 over x. And now we plug in infinity again, and we get cosine of 1 over infinity. And if you think about, remember what cosine of 1 over infinity, or what 1 over infinity is, basically. So this is really kind of me thinking here. And that's like cosine of 0. And so cosine of 0 is the number 1, which is exactly what we found when we were doing some of those review problems. But this time, we don't have to rely on our calculator. We can use the calculus with L'Hopital's rule. All right, so let's look at another example. Now these are new ones. We didn't do these at the beginning. They're a little bit trickier. So let's look at this one. So let's plug in infinity so you can see what happens. Let's go kind of slow on this one. So if you plug in infinity, here's what you get. So just wherever you see an x, plug in an infinity. So you can kind of then interpret it. So 2 times infinity on the bottom, and then 2 times infinity on top. And so I'll put this in quotes because it's really, I'm kind of thinking here. This is not equal to really, because infinity is not really a number. It's a concept. So what can I do? So what I have here is 1 plus 1 over 2 times infinity. So that's like 1 over infinity, which is like 0. So basically you have kind of like 1 plus 0 here. And then 2 times infinity, you can just write that as infinity. And so we wind up with 1 to the infinity. And so this is another type of indeterminate form. And I talked a little bit about this, but let's think about it again because it's important that you understand, oh, why is it an indeterminate form? And the reason it is an indeterminate form is because this 1 Right? If a number is bigger than 1 and you raise it to a big power, it gets bigger. But if a number is less than 1 and you raise a big power, it goes towards 0. It gets smaller. And so the question is, is it getting bigger? Is it getting smaller? Or somehow the 1 and the infinity, these, this is going to 1, this is going to infinity, is somehow are they canceling each other out, and is it going to some number? So what we want to do, our goal, is to take this 1 to the infinity and somehow turn it into either a 0 over 0 or infinity over infinity indeterminate form. And then we can use L'Hopital. And so at first it seems like, well, how can you get this to turn into that? And the trick of doing this is using e's and ln's, basically exponentials and logarithms, because what they basically do is they unlock exponents. So in a sense, whenever I'm working with exponential things, like this kind of thing here, I know I'm going to have to typically somehow use e's and ln's. And what that will do is it will unlock this exponent. Basically, it'll turn this exponentiation type thing into, if you want, in this case, a division type thing. It actually turns it into multiplication, and then we turn it into division. But you'll see. Okay, so let's just rewrite this. So what do I mean by using e's and ln's? We'll rewrite this as the limit as x goes to infinity. And I know that the e to the ln of the anything, right? So e to the ln of the anything is the anything by definition, because these are inverses of each other. So what I can do is I can rewrite this as e to the ln of 1 plus 1 over 2x, and that's raised to the 2x. And that's just an identity, right? Because e to the ln of the anything is the anything, so I'm just rewriting this. But what's nice is it turns this exponent right here, this exponent, and it can bring it down in front. So it turns this exponentiation into multiplication, which at first doesn't seem to be a big deal, but you'll see that you kind of unlocked the exponent here. And so it's e to the 2x times ln of 1 plus 1 over 2x. And so instead of looking at this thing, what we're going to do is we're going to look at this thing now as x goes to infinity. And once we solve this thing up here as x goes to infinity, you'll see you're going to get this to be equal to e to some number. All right, so let's go find that number. So that number, question mark, is equal to the limit as x goes to infinity of this 2x ln of 1 plus 1 over 2x. So now let's reevaluate our limit here. Let's see what we have. So now if you plug in infinity, what happens? So let's just plug it in, nice and slow. You get 2 times infinity ln of 1 plus 1 over 2 times infinity, which is equal to, so you're going to get infinity first, because 2 times infinity is like infinity. And then you have ln of 1 plus 0, so ln of basically 1. And we know what ln of 1 is. ln of 1 is like 0. Well, ln of 1 is 0. So you get infinity times 0. Oh, this is nice. It is still an indeterminate form. So you can see here we still have an indeterminate form, but it's a nicer indeterminate form in a sense. And we saw this indeterminate form in the last problem too. So this right here is an indeterminate form, infinity times 0, but it's much nicer than 1 to the infinity. And we worked with this type of problem in part A, and so what did we do? Again, the idea is try to turn this into one of these types of forms, 0 over 0, infinity over infinity. And so look, I'm going to leave this piece alone, and I'm just going to mess around with this x like I did last time. So what I can do is I can rewrite this as the limit as x goes to infinity. I have 2 ln of 1 plus 1 over 2x. And then divided by, so not divided by x, because that would change the expression, but if you divide by 1 over x, remember these two things right here, this and this, are exactly the same, basically. Especially when you're talking about limits, they are the same. And so here, if you multiply by the reciprocal, you get this back. But now if you evaluate this limit at infinity, what do you get? You basically get 2 times, let's go slow, 2 times ln, so you can see the work, 1 plus 1 over 2 times infinity, divided by 1 over infinity. And so then on top, what do I have? I have 2 times basically ln of 1, and ln of 1 is 0, so you get 0 on top. And on bottom, you have 1 over infinity, which is 0, which is perfect. This is one of my nice indeterminate forms, which I can L'Hopital. So we have another indeterminate form, but it's a nice one. It's a L'Hopital one. So we're going to use now L'Hopital's rule. So right here, this will be equal to then the limit as x goes to infinity of what? Well, L'Hopital's rule says you take the derivative of the top here, divide by the derivative of the bottom. So this will be the derivative of 2 times a function is just 2 times the derivative of the function. This is going to be a chain rule now. Derivative ln is 1 over. So 1 over, not just 1 over x, but 1 over whatever's in the inside. So 1 over 1 plus 1 over 2x. And then times the derivative of the inside. Now, the derivative of 1 over 2x, remember 1 over 2x can be rewritten, and here's where you have to be careful, it's 1/2 x to the negative 1, which when you take the derivative, this will become negative 1/2 x to the negative 2, which equals negative 1 over, let's say negative 1/2 times 1 over x squared. And so if you want here, we can write this as negative 1 over 2x squared. And then the bottom, we take a derivative of 1 over x. And we've done that before, but remember, it's not hard to do. It's like, oh, 1 over x is equal to x to the negative 1. So the derivative is negative x to the negative 2, which is negative 1 over x squared. And a lot of times I have these memorized by the time I do them, 3 or 4 times. And so this is the negative 1 over x squared. And so what's going to happen here, if you think about it, we can cancel some of this stuff off. You have a times 2, you have a divided by 2, so those 2's are going to cancel. You have a negative 1 over x squared, and you have a negative 1 over x squared, so this is going to cancel with this. And so then we're left with this to be equal to the limit as x goes to infinity of 1 over 1 plus 1 over 2x. And so now when I canceled these off, I didn't mention this before, but that was this indeterminate form, 0 over 0, going away. And so now if you plug in infinity, you should get out an answer. So 1 over 1 plus 1 over, I'll go nice and slow here, 2 times infinity. That's really me thinking. Which is equal to 1 over 1 plus 0. So it's just equal to the number 1. Now here's where you have to be careful, because a lot of times when I do these problems, they're so long, I'm like, I got an answer. That must be my answer. But remember, that's not the answer. That's what this thing is. And so up here, this is going to be equal to, if you want, e to the 1. Or if you want just e. So the answer is the letter e. Or the number e, I should say, right? Now, there is a nice way to check your work if you want to. You can check your work by simply coming back up here and plugging a very big number in for x. So for example, on your calculator, what's nice about this is I can plug in, let's clear this out, I could plug in like, let's do 100. So 1 plus 1 divided by, and then 2 times 100, so 2 times 100, in parentheses, and then raise it to 2 times 100. And I should get out a number that's close to e. So hit enter, and that's what I get out. Which, if you remember, e, so you hit second ln and raise the first power, is that number. So it's getting closer. If you plug in 1,000, I bet it'll be even closer. And so this is a nice way to kind of check your work. If you get an answer, you can easily check your work by using your calculator. All right, let's do one last one of these. So let's look at this problem here. And so on this one, let's see what happens when we plug in infinity. So here I plug in infinity for x, and so I get infinity to the 1 over infinity, which I'm like, well, is that an indeterminate form? Well, let's see, that's actually infinity to the 0. Oh, okay. So that is another indeterminate form. Indeterminate form. And let's make sure we understand why it's an indeterminate form. And the reason is because typically when you raise something to a 0 power, you get 1. But if you have infinity, which is a really big quote quote number, right? It's kind of like, oh well, it's getting bigger and bigger. So what's winning? Is to the 0 winning, or is to the infinity going to infinity winning? Or are somehow they canceling each other out and combining or something, if you want, and giving you out a number in a way. So again, the way we work with this is you're working with exponentials, so you're going to invoke e's and ln's to kind of help you. So this is the same as the limit as x goes to infinity of e to the ln of x to the 1 over x. And that's because e to the ln of the anything is the anything. But what's nice is it takes this exponent right here and you can move it down in front. And then think about it, what's happening is it's going to change this type of indeterminate form. So you're going to get the limit. It's going to turn this exponential type of indeterminate form basically into like a 0 over 0, infinity, infinity, or 0 times infinity type form. So that's kind of a nice thing. So the limit as x goes to infinity of e to the 1 over x, ln of x. And so this is going to be equal to, and it's going to be e to some number as x goes to infinity. We want to figure out what that number is, so we'll put a question mark here, is equal to the limit as x goes to infinity of 1 over x times ln of x. So now let's see what happens when you plug in infinity. So when you plug in infinity here, you get 1 over infinity times ln of infinity. And that's really 0 times infinity, which again is another indeterminate form like we did before. But if you look at this, it's like, oh, this is even easier because the idea is I want to turn this into a what? Either 0 over 0 or infinity over infinity type. And we've been doing lots of zeros over zeros. So it'd be nice to have an example where we're doing like infinity over infinity. And if you just come back here and look at this and just say, oh, I can rearrange this. Instead of doing this sort of multiplication here, what I can do is I can rewrite this as the limit as x goes to infinity. And I'll just put ln of x on top and x on the bottom. And now I got it. If you plug in infinity, you get ln of infinity, which is like infinity because ln grows. And then you plug in infinity downstairs, and the x, you get infinity. And this is one of our nice indeterminate forms that we can L'Hopital. So let's L'Hopital this indeterminate form, or let's L'Hopital this limit. So here, we're going to take it to the hospital to get fixed. And so this will be the limit as x goes to infinity. The derivative at the top is just 1 over x. Derivative of x is 1 over x. Divided by derivative of x is the number 1. And so this is just equal to the limit as x goes to infinity of 1 over x, which is equal to what? You plug in infinity, you get 1 over infinity. We can interpret that. That's simply equal to the number 0. Then be careful because that's not your answer, right? Your answer's up here. That's e to the 0, which is equal to the number 1. And the best part about these problems is you can check them with your calculator. So if you have a calculator, take it out, and all you have to do, you come over here and you say, okay, x is going to infinity, so plug in a really big number here. So we'll plug in, let's do 1,000. So 1,000 raised to the 1 divided by 1,000. Let's see what happens. It should be close to the number 1 if we did this right. Oh, and then 1.006. That's a good check. So I'm going with the number 1. So let's review real quickly what we just did here. We learned this new rule, L'Hopital's rule, which helps us evaluate limits if we wind up in this situation 0 over 0 or infinity over infinity. The rule says if you're in this situation, then you just take the derivative of the top and divide by the derivative of the bottom, and now take the limit, and the answer should be exactly the same as it would have been before. Then we take a look at these sort of more difficult indeterminate forms. And the idea of solving those is to take these and turn them into these up here, into 0 over 0, infinity over infinity. And so now basically you can evaluate any limit by hand. When I say by hand, you may be using calculus, but on your own in a calculus book.